We usually think of the internet as this boundless infinite space. You plug in a device, it gets an IP address, and you're instantly connected. It feels exactly like, drawing water from an endless well.
Right. You just turn the tap and the connectivity flows. It really does feel that way to the end user. It's just binary. You are either online or you're offline.
Yeah.
We take the sheer scale of that invisible plumbing completely for granted, every single day.
We totally do.
Yeah.
But the reality is that well actually ran dry. The internet literally ran out of space.
Yes, a very literal wall.
Exactly. So today we are taking a deep dive into a stack of CCNA networking materials. These are the actual blueprints and training modules that network engineers study, to keep the internet running. And looking at these documents, it is just wild to realize that the original architecture of the web hit a hard mathematical limit.
It really did. Every single one of the 5 regional internet registries around the world, so that's ARIN in North America, RIPE NCC in Europe, APNIC in Asia, LACNIC in Latin America, and AFRINIC in Africa, they have all officially exhausted their IPv4 address pools.
Wow. So they handed out the very last addresses.
Yep. The well is dry.
Okay, so the goal of this deep dive isn't just to memorize a new IT protocol or read a dense technical manual. We really want to understand how engineers took that exhausted system and rebuilt the internet's addressing architecture from the ground up to be smarter, faster, and infinitely larger for you, the listener.
And to really grasp that, we need a fundamental paradigm shift, because IPv6 is not just, IPv4 with more numbers.
Right, it's not just an expansion pack.
Exactly. It is a complete ground-up redesign. The engineers at the Internet Engineering Task Force used this massive transition to fix decades-old limitations in IPv4. So they added built-in auto-configuration and radically smarter address resolution that the old protocol simply never had.
Let's get a sense of the scale first, because we know IPv4 gave us about 4.3 billion addresses. And obviously we ran out of those. So exactly how big is this replacement?
Well, the scale is almost hard for the human brain to comprehend, to be honest. IPv6 expands the address space from 32 bits to 128 bits.
Okay.
And that gives us 340 undecillion possible addresses.
Wait, 340 undecillion? How do you even visualize that?
Well, just write down the number 340 and then put 36 zeros right behind it.
That is just staggering. It's literally like counting grains of sand on a beach.
Pretty much.
But knowing that, a huge question jumps out from the source material. We have this massive new system, but we obviously can't just flip a giant switch at midnight and move everyone in the world over all at once.
No, absolutely not. Doing that would instantly break the internet you rely on every day. There is no single cutover date.
So they just run at the same time?
Yeah, these two protocols are going to coexist for years, maybe even decades. And to make that happen safely, network engineers are relying on 3 main migration techniques. The first one is called dual stack.
Okay, so is dual stack kind of like being perfectly bilingual? Like, I picture a device just speaking both IPv4 and IPv6 simultaneously, side by side, and it just uses whichever language the local network requires.
It's very much like that. Technically, it's closer to having 2 completely separate brains processing the world at the exact same time. The hardware runs both protocol stacks independently.
That makes sense.
It is the most straightforward approach, assuming your physical hardware can support running both. But, you can't always guarantee that. Which brings us to the second technique, which is tunneling.
Okay, tunneling makes me think of the postal system.
Yeah.
Say you write a letter in IPv6, but the delivery network, like the trucks and the sorting facilities, they only understand IPv4. So you basically take your IPv6 letter, put it inside an IPv4 envelope, and send it across the older network infrastructure.
That is a brilliant way to picture it, actually. The router encapsulates the entire IPv6 packet inside an IPv4 packet just to sneak it across an older IPv4-only cloud.
Oh, so it just hides it.
Exactly. And once it reaches the other side, the router rips off that IPv4 envelope, and the original IPv6 packet just continues on its way.
Neat. And what's the third method?
The third is translation, specifically something called NAT64.
Okay, so if dual stack is being bilingual and tunneling is using an envelope, translation has to be like having an active human translator sitting right between 2 people who speak entirely different languages, right?
Yep.
Like you have an IPv6 only device on one side, IPv4 only server on the other, and this NAT64 box sits in the middle translating the conversation in real time.
Precisely. And the really underlying magic of these three methods is that you, as an everyday user, never experience a disruption.
Right.
You stream your video or send an email completely unaware that this massive global plumbing upgrade is happening silently in the background.
I love that. It's totally invisible to us. But it brings us to a very practical problem for the actual engineers. With addresses jumping from a tiny 32-bit format to a massive 128-bit string, how are human beings supposed to read or type these things without going crazy?
Right. I mean, it requires an entirely new format. An IPv6 address is written as 32 hexadecimal digits.
Okay, hex digits.
Yeah, and those 32 digits are grouped into 8 distinct sections, with each section containing 4 hex digits. Each section represents 16 bits. Network engineers affectionately call these sections hextets.
Hextets. That's actually kind of a funny name.
It is, and they are separated by colons instead of periods.
But even grouping them, that is a massive string of characters. If I'm an IT admin, I do not want to sit at a keyboard typing out 2001:0db8 :00000 :0000 and so on all day long.
Well, the good news is you don't have to. The protocol includes 2 primary rules for compressing IPv6 addresses to make them human readable.
Oh, thank goodness.
The first rule is that you can omit leading zeros in any single hextet. So if a hextet is 01IB, you just type 1AB.
Okay, that's easy.
If it's 000, it becomes a 00. And if you have a hextet made of 4 zeros, just 0000, you literally just write a single 0.
Wait, I have to ask about this. Dropping leading zeros makes total mathematical sense, like 05 is just 5. But why not drop trailing zeros? It seems like you could save even more space if you let people drop zeros at the end of the block, too.
It's a great question, but it all comes down to ambiguity. Let's look at the hextet, ABC. If we allowed you to drop trailing zeros, ABC could secretly mean ABCO.
Oh, I see.
Right. But if we also allowed dropping leading zeros, ABC could mean 0BC. Those are 2 completely different binary values.
Yeah, totally different numbers.
Exactly. If you drop a trailing 0, the computer's processor has absolutely no way to know which of those 2 values you intended. So the rule must be strict. Only leading zeros are safe to drop to preserve the exact precision of the address.
Ah, I see. So the computer needs a rigid rule so it can rebuild the address perfectly when it processes it. Okay, so what's the second compression rule?
The second rule introduces the double colon. You can replace any single contiguous string of 1 or more all 0 hextets with a double colon, which looks like this, just 2 colons side by side. So if you have 3 hextets in a row that are just 000, you wipe out that whole section and put a double colon in its place.
That shrinks it down a lot.
Yeah.
But I assume there's a catch. You can only use that double colon once in an entire address, right?
Yes, and for the exact same reason we just discussed ambiguity.
Right.
If you had an address with 2 separate double colons and the computer needed to expand it back out to its full 128 bits, it wouldn't know how many all 0 hextets belong to the first double colon versus the second.
Oh, because it wouldn't know if it was missing 2 blocks here and 3 there or vice versa.
Precisely. By limiting it to one single use, expanding the address becomes simple arithmetic. The computer just counts the hextets it can see, subtracts that number from 8, and it knows exactly how many 0 hextets the double colon is hiding.
That is super clever. So we know how to compress and read these massive addresses. But the source material throws a huge twist at us when we look at what these addresses actually do. In the old IPv4 world, your laptop usually just got one IP address. But in IPv6, your device is going to wear multiple addresses at the exact same time.
This is a fundamental change in how network devices behave. In an IPv6 ecosystem, a single network interface typically carries at least 2 unicast addresses simultaneously. It gets a global unicast address, or GUA, and a link local address, or LLA.
Okay, so I picture this like working in a massive corporate office. You have your global mailing address for the public, so anyone in the world can send you mail. That's your GUA.
Right.
But you also have an internal desk intercom number that only rings inside your specific building, and that intercom is your LLA.
That is a remarkably accurate way to visualize it. The global unicast address is globally unique and fully routable on the public internet.
So it's your real public IP.
Exactly. And right now, the global authorities are only assigning GUAs that start with the binary sequence 001. In hexadecimal, that means public addresses currently start with a 2 or a 3, specifically the range 2000 : to 3 AF
Oh, wow.
which is amazing because that massive range represents just 1/8 of the total IPv6 space.
Just 1/8. That's crazy. How is that global address structured, though? It can't just be a random string of numbers.
It's highly structured. It's usually broken into 3 distinct parts. First, your internet service provider assigns you a global routing prefix, which is usually 48 bits long. That prefix identifies your specific company or home to the entire internet.
Okay, so that gets the packet to my building.
Exactly. Then you have a 16-bit subnet ID, which your organization uses to divide up its own internal networks. Finally, you have the 64-bit interface ID, which identifies your specific phone or laptop on that subnet.
Okay, so that handles the public side of things.
Yeah.
What about that internal intercom, the link local address?
The LLA is completely mandatory. Every single IPv6 enabled interface must have one, and it is strictly usable only on the local link.
Meaning just my Wi-Fi network at home, for instance.
Right, your immediate local subnet. Routers are hard-coded to never ever forward a packet with a link local address off that specific network. These addresses always fall in the FA80:10 range.
Got it.
The brilliant part is, even if a network admin doesn't configure one, the device will automatically generate an LLA for itself the exact second it boots up.
Before we move on from address types, the sources briefly mention unique local addresses, or ULAs, in the FC00:7 range. To anyone listening who works in IT, those sound exactly like the private IPv4 addresses we use today at home or in the office.
Yeah, and if we connect this to the bigger picture of network architecture, it is absolutely vital to clarify a dangerous misconception here.
Uh-oh.
Yes, ULAs are for internal-only use within a site. But for decades, people have treated private IPv4 addressing as a security feature. They believe that because an address isn't public, it's magically safe from hackers.
Right, I've heard people say that.
Right.
I'm behind a NAT, I'm safe.
Exactly. But the Internet Engineering Task Force strongly stresses that private addressing was never meant to be a security measure. True network security comes from firewalls and proper packet filtering on your internet-facing router, not from simply hiding behind a private IP address.
Good to know. So let's bring this back to the everyday user experience. When you walk into a coffee shop, sit down, and open your laptop, you're online instantly. You don't have to ask the barista to manually type a 128-bit string into your computer.
No, that would be terrible.
Right. In an IPv4 world, a DHCP server just hands you that address. But how do devices get these massive IPv6 addresses so seamlessly?
This is where IPv6 truly outshines the old system. It has incredible self-assembling capabilities. Devices obtain their network information dynamically using special ICMPv6 messages.
How does that work?
Specifically, the local router periodically sends out a router advertisement or RA message to every IPv6 device on the network, usually every 200 seconds. If your laptop just booted up at that coffee shop and doesn't want to wait 200 seconds, it sends out a router solicitation or RS message, basically shouting, "Hey, I'm new here. Send me the network details right now."
Hold on. You're telling me devices are just piecing together their own addresses using these router advertisements. As an IT guy, that sounds like pure chaos. How does the network keep track of anything without a central DHCP server handing out the rules and assigning the IPs? Does DHCP just go extinct?
It doesn't go extinct, but its role changes drastically depending on how the network administrator wants to set things up. There are actually 3 methods for dynamic addressing in IPv6.
Okay, what's the first one?
Method 1 is called SLAC only stateless address autoconfiguration. In this scenario, the router simply sends the prefix in the RA message, and the client device builds the rest of its address entirely on its own. No DHCP server is involved whatsoever.
So that's the truly chaotic stateless one where the device is totally autonomous.
Yes, and it's highly efficient. Method 2 is SLAC plus stateless DHCPv6.
So a mix of both.
Exactly. Here, the laptop still uses SLAC to build its own IP address, but the router's advertisement message contains a flag that tells the device, "Hey, go talk to this DHCP server to get some extra information," like a DNS server address.
Oh, so the DHCP server isn't giving out the IP?
Right. In this method, the DHCP server isn't tracking who has what IP address at all. It's strictly handing out the extras.
And I assume method 3 brings back the control.
Exactly. Method 3 is stateful DHCPv6. This is the closest to the legacy IPv4 experience. The DHCP server hands out the full 128-bit IP address, tracks exactly which device has what, and provides all the DNS info.
But there's a huge unbreakable rule here for all 3 methods, right?
Oh, a critical rule. No matter which of those three methods the IT admin chooses, the device's default gateway always comes from the router advertisement message itself. It never, ever comes from a DHCPv6 server.
Wait, really? Never?
Never. The router essentially broadcasts, I am your gateway to the internet. Use my link local address to leave this network.
That's fascinating. Let's zoom in on that autonomous SLAC method for a second, though. If the router hands my laptop the first half of the address, the 64-bit prefix, how exactly does my laptop figure out the second half, the 64-bit interface ID, all on its own?
Well, there are two main ways a device does this. The traditional method, created by network engineers, is called the modified EUI64 process.
EUI64, okay.
Yeah, and it's quite clever. It takes the device's unique hardware MC address, which is burned into the physical network card by the manufacturer and is 48 bits long, and it mathematically stretches it into 64 bits.
How exactly do you stretch a physical hardware address? That sounds impossible.
Well, you split the 48-bit MSC address right down the middle.
Okay, so two halves.
Right, into two 24-bit halves. Then you insert a very specific 16-bit value fifth in hexadecimal right in the dead center.
Like a wedge.
Exactly like a wedge.
But
finally, you look at the 7th bit of the very first byte and you flip it. If it was a 0, it becomes a 1.
wait, why flip the 7th bit specifically? What does that accomplish?
In Ethernet architecture, that 7th bit is known as the universal local bit. It tells the network whether a MASI address is a globally unique address assigned by a manufacturer or a locally administered address spoofed by an admin.
Oh, I get it.
Yeah, by flipping that bit, the IPv6 protocol is signaling to the rest of the network that this interface ID was legitimately derived from a physical, universally unique MS address.
So it literally hard codes my physical hardware's unique identity right into my public internet-facing IP address.
It does, which is incredibly useful for network engineers trying to track down a specific rogue device on a massive corporate network.
But wait, that sounds like a massive privacy issue.
It absolutely is. And modern operating systems, starting with Windows Vista actually, recognize that permanently linking your hardware identity to your public IP is a privacy nightmare.
Yeah, anyone could track your laptop everywhere you go.
Exactly. So they use the second method, randomly generated interface IDs. Windows will securely generate a random 64-bit number to combine with the prefix instead of using your MSE address.
But if billions of devices are just randomly guessing their own IDs, how does my phone know another laptop in the coffee shop didn't randomly guess the exact same number?
It performs something called duplicate address detection, or DAD.
DAD.
Nice. Before it actually uses the address, it sends out a probe to the network, essentially asking, hey, is anyone already using this address? If no one replies, the device knows it's safe to start using it.
Which naturally leads to another question. If devices are constantly probing the network for duplicate addresses, sending solicitations, broadcasting advertisements, wouldn't that create a deafening amount of traffic? In an IPv4 world, that would just flood the network with noise.
It absolutely would cause a flood in IPv4, but that's because IPv4 relies heavily on broadcast traffic. IPv6 solved this by completely killing the broadcast address.
Wait, totally did.
Totally. It simply does not exist in the IPv6 protocol.
Wow. You know, I always thought of the old IPv4 broadcast like a manager standing up in the middle of a crowded open plan office and just shouting instructions on a megaphone. Every single person in the room has to stop what they're doing, process the announcement, and decide if it applies to them, even if it totally doesn't.
That's a perfect analogy. Broadcasts force every single device on the network to waste precious CPU cycles inspecting traffic that probably isn't meant for them.
So annoying.
Exactly. Instead, IPv6 uses multicast, specifically the FS0::8 prefix range.
Okay, so how is multicast different?
Multicast is like sending an email only to a specific department's mailing list. Only the people on the list get the notification. We have the All Nodes multicast group, FS02::1, which reaches every device, and the All Routers group, FSJO2::2, which only routers pay attention to.
The sources talk about something even more targeted, though. The solicited node multicast address. How does that keep my laptop CPU from getting interrupted by network noise?
This is a brilliant piece of hardware synergy. A solicited node multicast address maps directly to a special Ethernet MASI address.
Oh, at the hardware level.
Exactly. Because of that mathematical mapping, the device's network interface card, the physical NIC hardware on the motherboard itself, can inspect the destination MASI address of the frame as it arrives on the copper wire.
So before the computer even really thinks about it.
Yes. If it doesn't match the specific multicast group the computer joined, the physical hardware drops the frame instantly. The computer's central CPU never even knows the packet existed.
That is incredible. The hardware itself does the filtering for you, preserving your battery life and processing power.
It is so much faster, smarter, and radically more efficient than the old megaphone method.
So we have all this efficiency, all this massive scale, and it culminates in what I honestly think is the biggest reward for any IT professional listening to this. Subnetting is finally easy.
It really is the ultimate payoff. Because IPv4 subnetting was an afterthought. It was bolted onto the protocol years later when they realized they were running out of space.
Oh, I remember the absolute pain of IPv4 subnetting. You had to borrow bits from the host portion of the address, draw out those positional value tables on a whiteboard, and do complex binary math just to figure out where your network ended and the next one began. It was a nightmare. But looking at IPv6 subnetting, it feels like just watching the odometer on a car roll over.
Because it is. IPv6 was designed with subnetting built in from day one. Remember that typical global Unicast address we broke down earlier?
Yeah, the one with the 3 parts?
Right. It has a dedicated 16-bit subnet ID field sitting right there in the middle of the address. You don't have to borrow any bits from the host portion. And if we do the math 2 to the power of 16, that gives you 65,536 subnets right out of the box.
That's huge.
And every single one of those subnets supports 18 quintillion individual hosts.
So if I'm assigned a network prefix, say 2001:db8:cad:/48, and my boss tells me to create 5 subnets for different departments, I don't do any binary math.
None whatsoever. You literally just increment the hexadecimal value in that subnet ID field.
Just count up.
Just count up. Your first subnet is 0001, the next is 0002, then 0003. You just count 0009, 1000A, 1000B, all the way to 1000F, and then just like a car's odometer, it rolls over to 000. Address conservation is completely dead.
It's so dead that the sources say even if you have a point-to-point serial link between 2 routers, like a physical wire that only connects 2 devices and literally only needs 2 IP addresses, you still assign it a full /64 subnet.
Think about that. You are giving 18 quintillion potential addresses to a single wire that only connects 2 routers.
Just because you care.
Exactly. It keeps the routing tables perfectly clean, the mental design simple, and you will still never, ever run out of subnets.
It's a completely different world. Let's bring this all together. We started with this cramped, exhausted space of IPv4 where the well had literally run dry. And we've seen how engineers use the crisis to build a massively scalable, self-configuring, highly efficient ecosystem.
Yeah, it's quite the journey.
We have dual stack and tunneling keeping the legacy web running. We have SLAC letting devices autonomously build their own addresses. And we have multicast hardware filtering, keeping the network whisper quiet.
It truly is an elegant, future-proof solution to a mathematical problem that threatened to halt the growth of the internet entirely.
But I want to leave you with a final thought to mull over. Building on exactly what we've learned today, we talked about how IPv6 devices can use SLAC to automatically generate globally unique, routable addresses, and how the traditional EUI64 method mathematically bakes your permanent hardware MC address directly into your public IP.
Right, which provides an unbroken, traceable link directly back to your physical hardware.
And we also talked about how NAT, that translation layer that accidentally acted like a privacy shield for decades by hiding multiple internal devices behind one public IP, is no longer necessary in IPv6.
It's a completely end-to-end connection now.
So imagine the internet of tomorrow. Every single light bulb, every smartwatch, your refrigerator, your car, they can all instantly generate a globally unique public address without a central server. When the well of connectivity is truly infinite and every single drop can be traced right back to the physical hardware in your pocket, what does that mean for the future of digital privacy and identity?
It completely changes the paradigm of anonymity, doesn't it? We are trading the friction and cramped quarters of IPv4 for the radical transparency and infinite scale of IPv6. It's a fascinating trade-off.
Definitely something to think about the next time you connect a new device to your network.
Thanks for joining us on this deep dive.